Okay, it's time to begin. I see everyone here except for Hannah. Okay, we pick up after a long weekend. I don't know about you, but yesterday was a really long, hard day of... Oh, wait. You've been here... Oh, no, you just walked in. That's right. It's Hannah that's missing. I just saw it. Yeah, yesterday was a long, hard day of grading. Very long day of grading. And I still didn't get the labs graded. I so need a TA. But hopefully you might have had a little more rest than me, especially noticing that there wasn't any homework due for tomorrow. It's just the thing from Friday carryover. We're going to do some math today. The math that we're going to end with, assuming we get to the math I plan on ending with, is more intense than the math you're going to have in the class, just showing you where it can go. So we're going to look at how we got the kinematic equations. We're not going to re-find the kinematic equations because we did that the first day of class. But we have just basic things about what calculus means. Remember I said that in the... I should have changed the font on this so the V looked nicer. In the algebra-based class, we say that the average speed is equal to the change in position over the change in time. So if we want to find the instantaneous speed, we take the average in the limit of an instant. So in the limit as the delta t is smaller and smaller, you're getting closer and closer to an instantaneous speed. And to actually get to that instantaneous speed, we have to shift from calculus where we change it from delta t to dt. What's the difference? The d means in the limit as delta whatever approaches 0. So these two, well, all three of the terms there, you have two equal signs, are identical in meaning. The speed is the limit as delta t approaches 0 of delta x over delta t, which is identical to dx dt. So that's what the difference is in calculus and algebra. All the rules we've learned in calculus are simply how to do things like that, and instead of having to do all the hard work, we just use rules we've learned. You guys probably all remember the first time you did a derivative, right? You did function of x plus, delta minus function of x all divided by delta. Yeah, we don't do that all the time simply because it's a lot of work and we've learned rules about how that math is going to play out. And so we'll be using calculus a lot. We'll never refer back to these rules again, but I just want to make sure people remember where it comes from. So here we have acceleration showing the same variation. Acceleration is dv dt to find the instantaneous acceleration. So let's go straight to something that's kind of a practical example. It's a practical example, except that I just made up this equation for the speed. Right? So you hopefully will have at least one homework problem that's, I say hopefully because I have to find one, that's due on Friday that will have something akin to this. An equation that's a calculus equation for velocity as a function of time, or potentially position as a function of time, or acceleration as a function of time, and then ask you to work with it. The reason I did velocity is because that's the middle of the three. So if I have this equation, and I ask you the question, how can you find the instantaneous acceleration at any time? How would you answer Hannah? The question right here. How would you find the instantaneous acceleration at any time given this equation for the speed at any time? Assuming one dimension, so speed, velocity, interchangeable.
I have a scrambled answer in my head, but I can't really do it.
Okay. Can you unscramble, Anne? Okay, so we'll just say the acceleration is dv dt. Now this here, what rule are we going to have to use in calculus to do that derivative? the product rule. So I will just take the first times the derivative of the second plus the derivative of the first, and this time around I'm going shortcuts here, not writing down, bring down the 2 times 10 raised to the 2 minus 1, multiplied by the second. And yes, we could simplify this a little bit. We could simplify this to factor out a 10t e to the minus 0.7t, and then we would have minus t plus 2. Yeah. That should have come out correct, right? Oh, yeah, I lost the 0.7, didn't I? Minus 0.7t plus 0.2. Better? Okay, so we were able to find the acceleration at any time. So, step 1, done. Michael, when is the speed the greatest? Now, I don't expect you to say at time equals 3 seconds or something like that. How do you find it? Okay, one way of doing it is to graph it. I actually, on the next slide, did that. It's going to come up. It's gonna. There it is. So I graphed it. And so we can say, okay, it must have a maximum speed right about here, which would be about 2.8 seconds. How do we do it analytically? Toussaint. Let me start with the simplest question. What aspect of this graph told me where the maximum speed came? Right, when you look at this graph, how do you identify where the maximum speed is? There are 2 potential answers. I'm obviously looking for one of those 2. Okay, Sally wants to answer.
Isn't it when acceleration is 0? Or
okay, when acceleration is 0, what does that acceleration 0 mean on this graph?
that it's changing direction.
Okay, that the slope is 0. So Vmax when the slope, which is the acceleration, equals 0. And so what we do is we take the derivative of this, the acceleration that I just did on the previous page, and we say, at what time is that equal to 0? So going back to the previous page, we have our equation here that says acceleration equals 10t, and I'm going to use 3 colors to write this equation. I'm changing the order here so I don't have a leading minus sign. It just makes me unhappy to have a leading minus sign. Okay, I wrote this in 3 colors. Ryan, can you tell the class why I wrote it in 3 colors?
Separate terms.
Oops, wrong place. Okay, your answer was correct. They're all separate terms. My condition for finding when I have the maximum speed is going to be when the acceleration is 0. So I put A, and I should have put this here, A at t max is equal to 0, and I have 3 different terms. This would be 0 when any color is 0. So I have 3 possible solutions. my red solution is going to be 10 t sub m equals 0. My green solution will be e to the minus 0.7 t sub m equals 0. And my blue solution is 2 minus 0.7 t sub m equals 0. 3 different solutions. Now, when I looked at the graph, how many places did I mark for the maximum speed? Just one. But yet I have 3 here. Why do I have 3 solutions here when there was only one maximum speed time? Okay, the slope is 0 when you have a maximum or a minimum, a local maximum or a local minimum. Also, it can be at an inflection point where you're just going like this. So we have to evaluate each one to see if it's a maximum or minimum. Mathematically, how do you evaluate? Well, let's do that later. Let's go get our answers. So, Tori just answered that question. It's your turn, Chad. Chad, what? You act like this is not a good thing. It's a really easy thing. At what time is the red equation going to be 0?
When t equals 0.
Yeah, that wasn't very tough. Okay, so there's one possible solution. Now let's just go straight to the other one, the next one, Jaron. At what time is e to the minus 0.7 tm equal to 0?
The negative 0.7 tm root of e.
This one here is a little more esoteric. Does anybody know the answer? You want to blurt it out?
I mean, it's either not, or you could say maybe negative infinity.
It's actually positive infinity because we have the minus sign in the exponent.
Okay.
So this approaches 0 as time approaches infinity. Okay, so we have 2 answers there. As you might guess, neither one of those are the answer we were looking for. And so finally we go to our third one. Back to Hannah. What time is this equation going to be true? And doing long division, that's going to be somewhat less than 3. What is it?
2.92. That's a guess.
Okay. Yeah, 6, so.
2.85. 2.86.
Okay. So we have 2.86 seconds approximately. Yeah. I'm happy with just 3 sig figs here and moving on. So we have 3 possible answers. We know logically that it's not the time equals 0, not the time equals infinity, so it's got to be the 2.86 seconds. But how would we now test that mathematically?
Plug them back into the original equation.
Okay, we can plug them back into the original equation and see what the values go to. So the value for velocity or speed at time equals 0 is going to be 10 times 0 times e to the 0, which is 1. So that's clearly 0. So speed is 0 at time equals 0. Question? That was another one, but I'm going with the first answer. Yeah, that if you had said that, I would have gone to the graph first. Okay, the next one I'm going to do, time is infinity. Time is infinity. I have, infinity squared times e to the minus infinity, which is 0. So I have an infinity times a 0. And then I have to do something, like, say, L'Hopital's rule to determine what value it's going to go to in that limit. The other way of doing it, besides the graph, I'll go to the graph because it's easiest to explain by the graph, is looking at the curvature. How do you look at the curvature mathematically? You take the second derivative. If I take the second derivative of my velocity equation, if the second derivative is positive, that means that the slope is going to be increasing, which means it must be at a minimum. If the second derivative is negative, that means the slope must be decreasing, it must be at a maximum. When I was, I swear this was when I was in high school, my math teacher taught me this to remember. So if the second derivative is positive, then it's at the bottom. If the second derivative is negative, it's at the top. Did you guys learn that? No. That's how I learned it. I learned that rule before I learned the logical sense. Oh, so if the second derivative is positive, that means that it's going to be going up as you move away on both sides, and so it must be a negative. I learned that later. So looking at the graph, we could have seen the curvatures, taken the second derivatives, we get a mathematical value for the curvatures. So we now know quite specifically this here. I had said 2.8. Well, now we know it's a little beyond 2.8. But we have the answer to the time when the speed is max. When is it at the greatest acceleration? How would you find the greatest acceleration? We're not going to do this, by the way, just because it's...
Second derivative again?
Yeah, we got the acceleration equation. We want to maximize acceleration, so we take the derivative of the acceleration equation, find the times when that is 0, and those will either be the greatest positive or the greatest negative accelerations. And how far does it travel in 10 seconds? As far as it travel in 10 seconds is a different question than everything else we've been doing. How do you find the distance something has traveled? We're going to have to integrate that. We have the relationship that dx dt equals v. So if I separate variables, I'll have dx is equal to v dt as long as v is just a function of t. Integrate both sides, and I get my distance. Looking at the picture of the graph, what is the equivalent to integration in terms of the picture? The area under it. So the area that's under this graph is the integral. And when you first learned integrals, I remember very clearly my teacher trying to explain this and me sitting there slack-jawed. If I'm going to add up the area, I'm going to take a little slice here and take its height, and a little slice and take its height, and a little slice and take its height. And that's what the whole integration thing means. This symbol means sum. Kind of looks like an S because it's supposed to be an S. It means sum. This is the other symbol for sum. This one here is just a discrete sum. And this is a continuous sum. So when you do a discrete sum, you do something like sum for I equals 1 to infinity of x sub I, right? That's how you write it out. Well, if you're going to do a summation for a continuous thing, you write it as the sum of your function, which is the value on the vertical axis, times the width on the horizontal axis. So each one of these little slices has a width of dx. Now, how big is the value dx? Infinitesimal. It's not like it's 0.01 for each one. It's infinitesimal width. But that's why you have the dx here, because you actually have a width times the height. And then you're summing up that product when you're doing the integral. And so I want to find the area under this. Now, if you look at this function, it's asymptoting to 0 as x approaches infinity. So you might ask yourself, so is it going to be finite or infinite? Because it never actually reaches 0. Well, we answer that by doing an integral. So how do we do this integral? You know what? I'm not going to do it. I'm not going to do it just because I would either have to use the integral table or do integration by parts twice. Since it's a t squared, I could do integration by parts once and get down to a t, do integration by parts a second time, and then be able to do it. You guys probably have done that in class, right? But I would just have my integral dx from x0, which I'm going to say start at 0 position, to x final is equal to the integral dt from t0 equals 0. I forgot to write the 0 there. To t final of 10 t squared e to the minus 0.7 t dt. And then I would have to do that integral on the right, and I would get my answer. And after you do the integral, you would see, is it finite or infinite for the distance. But if we go out to only 10 seconds, it's of course going to be finite. It's if you go out to infinity that you have the question. And so out to 10 seconds, looking at this graph, you could try to estimate, like say, I'm going to make a straight line approximation to this graph. My straight line approximation goes like, I'm just trying to make my line so I have about the same amount over as under. Okay, I'm going to be too high, right, with this graph because there's more time above the line than there is where the line's below my curve. But then I could just take the areas of those and I would have an approximate value, right? 1/2 base times height. So you would have 10 is the base, the height is 12, 1/2 of 10 times 12 would be about 60. So that's my estimate for the distance it would travel. But you could do the calculus and get it right. Moving on. Moving on to something that's actually this is the picture that goes with the integral. Yes, Ryan.
If we were to take that integral, we would wind up with a constant c. You usually just use like a 0, initial condition.
Well, you do the integral from 0 to 10 seconds.
Oh, you did a definite integral.
Yeah.
Okay, that makes sense.
Okay, so that picture was just going with how you do the integral, the graphical thing. Now, a more practical problem. A dragster, here's some real values. The acceleration for dragster, according to what I read, is 39 meters per second squared is the maximum acceleration. That's right about 4 Gs. So they get pushed back in their seats pretty hard. The top speed that a dragster reaches they don't do the quarter mile anymore. I'm old. They changed it from quarter mile to 1,000 feet in 2012. But the top speed that they'll hit in that 1,000 feet is about 330 miles per hour or 148 meters per second for a top fuel dragster. So we have a realistic situation, the acceleration far greater than the acceleration if you just drop something, and the top speed. And then I want to try to model that to figure out, what is its acceleration as a function of time, and from that, what's its speed as a function of time, and so on. Now this equation, okay, I can do this still in the line option. There, I put a square around that equation. That equation is actually a sound starting point. When we learn about Newton's second law, which will be approximately tomorrow, this equation makes sense because you have the air resistance, which at slow speeds is proportional to the speed something's traveling. And so this equation is consistent with what would happen at slow speeds. Now the problem is at high speeds, the equation changes. And so this may not be a perfect solution, but it's a start. Now, if you look at this equation for acceleration, what's the thing you notice that doesn't fit with anything we've done? There's something about this equation that doesn't fit with what we've done. What? Okay, we have the acceleration is initial acceleration, and it's a function of what variable? Velocity. What have we been doing? Of time. So this is a function of, shall we say, the wrong variable, not the one we've been using at the very least. But this is, like I said, for slow speeds, it should be the correct equation. And so I ask, based on this model, what's the speed as a function of time? How can we even approach a problem like this? There's no time written in it. How do I find as a function of time? I'm looking for ideas.
The velocity and then put the velocity in some equation?
Okay, plug in.
Or find the plug in. I don't know. Never mind.
Okay, what variables do I have? There are two constants, the number 1, and two variables. So what are the two variables? Acceleration and velocity. We have learned a relationship between acceleration, velocity, and time. So we should be able to use that relationship to get it in terms of time. So that's where I'm going to start. I'm going to start with acceleration is dv dt. So if I just substitute for the acceleration, I will have eliminated acceleration while introducing time. Hopefully I put Vmax there, yeah. I had written something else originally and then changed my mind about what to write. So, if I look at this equation and just the part inside of this box, then my two variables are v and t. So if I've already changed the variables to what I want, but I still have to solve it for v. So the first step was seeing how to get the variable switch. Because when you look at it, it's not obvious the first time you've done it. After you've done it, it becomes more obvious. So now I need to integrate this beast. What steps do we need to take before we can integrate? Okay. The name for the step is separation of variables. We need to multiply both sides by dt so that we have the d's on top on both sides. And then we need to rearrange so we have only v's on one side and only t's on the other. So there's a lot of ways to do this, but one way that's going to make it easiest for us. And so I'm going to go through what looks like a little extra work just to make it easiest for us. I'm going to write this as dv equals dt times now, what I do, I multiplied, or I factored out the 1 over Vmax, which meant that this one had to be Vmax over Vmax, so there's a Vmax there. And now I'm going to change the sign and divide. So I'm going to divide everything by V minus Vmax. And you might ask, why did you change the sign? Why did you do that? And we'll see in just a moment. So when I do that, I'm left with dv over v minus vmax equals minus a0 over vmax dt. Now the reason I did it is when I integrate the left side, I'm going to integrate from v initial equals 0 to whatever v final is, and from time initial equals 0 to whatever, whoops, that's not, whatever the final time is. Over here, I'm going to use a u substitution. Now, before I do the u substitution, why did I say v0 equals 0?
Because the velocity starts at 0.
Yeah, it wasn't an arbitrary decision. It's because when I have a drag race, it's understood you start at rest. You don't have a rolling start in a drag race. And so v0 has to be 0 for the drag race. So at time equals 0, when the Christmas tree turns green, the speed was initially 0. Now, I said I'm going to do a u substitution, and so I will make the substitution that u is equal to v minus v max. So du is equal to dv. And I have the integral. And I'm going to put from u0 to u final. I'm not even going to put what they're equal to right now. It's just easier to put it back in later. Of du over u equals the integral t0 equals 0 to t final minus now I do the integrals of both sides. Well, what's the integral of the left side? It's going to be natural log of u. And so I know I'm going to a new page and you can't. This program actually works great. You can just scroll continuously through pages unless you start with a PDF. I think it's a memory restriction that doesn't allow me to scroll smoothly through the pages. You had a question? Did you have a question? No, okay. So on the left side I have natural log of u from u0 to u final equals, and on the right side, that was minus a dot over v max t from t0 equals 0 to t final. Taking those limits for the natural log, that's going to be, well, I'll write it out long form for people who want to see that. There I wrote it out long form. You may or may not be aware that the left-hand side of my equal sign is right now mathematically nonsense. Mm-hmm. Okay, so Chad agreed with me. Why is it mathematically nonsense?
Because u naught, or u naught, that's actually v naught minus v max.
Yeah.
Which will go negative.
Actually, should be, yeah, actually both of them will be negative. I shouldn't have scrolled. Okay, so one thing is I have natural logs of negative values, which is nonsense. But there's another thing that's also nonsense that's even more obscure.
Well, I was just going to comment on that. If I'm not mistaken, it's absolute value of u that we kind of registered on that.
Yeah, I honestly didn't pay attention to that because it's not a problem in real life. The other problem is you can't take the natural log of speed. Speed has units. Natural log is an infinite series polynomial. You can't have units as the argument for natural log. It has to be a unitless argument. You can never take the natural log of 10 meters per second. But you can combine these into natural log of u final over u initial because we have the subtraction. And now, suddenly, both of those problems disappear. Now, it's all going to be copacetic. So, I better plug in what my u's were now. So, my u was v minus v max. Go ahead.
On the right, is that supposed to be negative a or negative a naught? And if it changes from negative a naught to negative a, why did it do that?
That answer? It's because I forgot to bring it down. 2 places. Thank you. And I forgot to write the t final there as well. Now I'm going to go ahead and substitute for v final, I will just put v. For t final, I would just put t. The reason I had the finals as subscripts was because I can't have the limit of integration being the same as the variable of integration. Likewise, I'm going to substitute my v0 was 0. And so what I have on the left side is natural log of v minus v max over minus v max, which looks horrendously bad until we realize that if I multiply top and bottom by -1, it's perfectly fine. what should I do now if I'm trying to solve for the speed? I have the speed inside of a natural log. So what do I do if I want to? I do what? Okay, I do the exponential on both sides because that's the inverse function of natural log. Remember that e to the ln of x is just equal to x. That's what the inverse function means. And so I do raise both sides, e raised to those powers, and I'm left with on the left side now I'll multiply both sides by minus v max, so I have and finally, to solve this for v, actually I say finally, this is my penultimate step. Because I can factor out the Vmax. Now, if you look at this equation, it's now the speed is a function of time, and we can think about this, what this means logically. At time equals 0, what does e to the minus 0 equal? 1. So at time equals 0, this thing in parentheses is 1 minus 1, 0. So it's going to start at a speed of 0. Kind of important because that was one of our conditions we started with. And as time increases, this function here is going to exponentially drop. And so we have 1 minus an exponential drop. Our speed is going to rise asymptotically to approach Vmax. There's my asymptote. And so it's going to go like this. So that's what my equation for speed as a function of time looks like. Now, does that seem realistic for a dragster? When you look at this, what does it tell you about the acceleration?
It's very rapid and it tapers off.
Yeah, it starts with a high acceleration and then it slows down to your lower acceleration. Right, so when you look at this, we have enough understanding from lab last week and continuing with the lab this week to understand how to interpret this, what it means. We have an equation for the speed as a function of time. Now, I asked you for more than just the speed as a function of time. I also asked you, what's the acceleration as a function of time? Now that I have the speed as a function of time, how do I find the acceleration as a function of time? I take the derivative. So, with this speed as a function of time, to find the acceleration as a function of time, I simply take the derivative of it. There. Now you know that I have a new page. And so I'll rewrite at the top here. That was my speed equation. By the way, what do I have to have for units of my exponential function?
Say that again.
What do I have to have for the units of my exponential function? E raised to, and then what are the units of the thing it's raised to?
Won't they all cancel out because meters per second squared over meters per second times second?
It has to be unitless. Once again, if you have units in your exponent, you have an untenable situation. And so that has to be unitless. And so she already did the calculation in her head. Acceleration is meters per second squared. Multiply that by time, that'd be meters per second. Divide it by speed, meters per second divided by meters per second, and it's unitless. Always a good thing to check the units. I haven't mentioned this in the other class, and I really should have. Some people are going to, let's say, try to go to medical school, and they have to take the MCAT. And sometimes you'll have questions on the MCAT where all of the numbers are the same, and it's just the units are different. They're testing to make sure you understand how to evaluate the units. And by evaluating the units, you can often tell, ooh, I must have made a mistake. So you'll notice that when I do problems, when I model problems in class, I keep the units in there because then I can see if the units don't match, I made a mistake somewhere. And yes, I do make plenty of mistakes, right? We're all humans. So funny. Before I became a teacher, well, my first year as a teacher, I was speaking with the person who had taught the year before me. He was a dentist who had been contract teaching. And he had a couple weird ideas. Number one was apparently he made a lot of mistakes in class. And he said, but that's good, because the students need to know that nobody can do physics, not even the teacher. Yeah, I was like, whoa, really? No one can do this stuff? I mean, it's only general physics. You know, it's hard for the beginner, but it's not the advanced stuff. And then he went further. Since nobody can learn physics, it's just not possible. He actually would have a review session the night before the exam in which he went over every problem that was on the test. And then the next day they would get the test with all the problems that they'd studied the night before. And so his grades were almost all A's and a few B's. And he got nasty letters from people who got B's that said it wasn't fair they didn't get an A. He told me all of this while he was working on my teeth, and I was getting more and more nervous as time went on. Because, you know, you can do physics, and hopefully he could do, you know, dental work as well. But, yeah, his attitude's scared me. Okay, so I wanted to find the derivative of this. So to take the derivative, dv dt equals Vmax times 1. What's the derivative of Vmax times 1? 0, okay. So we nail that one. And then I'm going to have minus Vmax times, and I have to just bring down the derivative of the exponent, so that's minus and so I have minus and a minus makes it a plus. And so there's my acceleration as a function of time. That wasn't so hard. I didn't even do that in preparation for class because I figured, oh, that's going to be easy. So if it hadn't been easy, then I would have, you know, been scratching my head saying I should have done it beforehand. What about going the other way? How do I find the equation for the position as a function of time? Have to integrate. So I go back to v is equal to dx dt what am I going to have to do to integrate this thing? Okay, multiply by dt. Excellent. Then what? Come on, Hannah, put us on the right track. It's only one more step. Then integrate. Because it's already, variables are separated. Only x on the left side, only t on the right side. So now I just have to integrate this baby. So I integrate this baby and I get, obviously you start at a position of 0 in your drag race. I'll bring the Vmax outside since it's a constant. have to have the parenthesis, or else you have nonsense. You have to have the dt. And we integrate this. So integral of 1 dt is just t. Integral of e to the minus a over v max t is going to be divide by the derivative of the exponent and then I put in my limits. Now, when I put in my limits, we have to be careful on the right-hand side. The left-hand side, I already put them in. It was so simple. But on the right-hand side, put in the first limit. That's going to be t final. Notice minus and minus is a plus. So there's the upper limit. Now I subtract the lower limit, put in 0 for t, that's 0. But what do I get when I put in 0 for t in the second one? Hopefully I didn't forget more. That zeros are bedoubling me apparently. I wouldn't have even remembered if I hadn't had to been corrected earlier. Okay, so we have this thing here, of course, the 0. I'm just going to erase the 0. It just seems to get in the way. And there's my equation for x as a function of time final.
Should that last one be negative or positive?
It should be a negative. This here was a minus, so it was plus. And then you subtract the lower limit, so that's why it's minus. So here's my equation for position as a function of time. Fairly long and drawn out. I finally erase all my f, so it'd be at any time. And oops, erased too much there. So I have my position now as a function of time. My position is v max t. Well, that makes perfect sense. No. Plus this, minus this. It's a pretty long, hairy equation. Then I asked you the tough question. I asked you to find how long it takes the dragster to complete the race, that is to go 305 meters, with our equation here. So I need to solve this equation for the time if x is equal to 305. Question?
Yeah, in your equation there, I came up with a Vmax squared.
Did I make a mistake somewhere there? There's a Vmax out front.
Oh, you separated it. And I didn't, yeah.
Yeah,
Okay.
so you do have Vmax squareds in there.
That wasn't there.
It's just that I put it out front.
I was looking down too much. Okay.
Without asking people questions that make you all scratch your head and say, I can't do that, you cannot analytically solve for time. I know I changed the lowercase. I think I got the emphasis out of the way. You cannot analytically solve this for time. Why? Because I have a linear time right here and an exponential time right there. And there's no mathematical way of getting those into one equation, time equals this. Have you guys ever encountered such a transcendental equation?
Can you say that last part again? You can't do it for what reason?
I don't know why I'm writing this since the next few slides have that at the top. Because you have this here is a linear term, and this here is an exponential term. You can't solve for having both linear and exponential in the same equation for that variable. But I have x as a function of time, not a problem at all. But time is a function of x you can't do.
Doesn't the time cancel out with the other stuff in the exponential though?
No, because we want to find a specific time for a given x. So with a transcendental equation like that, one that you can't solve analytically, the way I like to do it is graphically. So here's the equation, just in case I'd made a mistake, and here I have it written out the way Chad has written his, where I separate each term so I have Vmax squared over out instead of having it factored out, right? That's what you had? Mm-hmm. And I changed the order so the negative term is is in the middle. I rearranged that so I have a left-hand side that's a linear equation in time and a right-hand side that's an exponential equation in time. Now, you can use something like a spreadsheet and find the time where those two equal each other, or you can just do it graphically. Graphically is the one that logically makes good sense. I just say A is equal to this thing, and I'm changing colors in case you're wondering why I erased. B is equal to this, and I plot A and B versus time on the same graph, which looks like, yeah. And so here we have the left side of the equation is in blue, that's the linear part. The right side of the equation, the exponential, is in red, and you can see that they cross right here. So I could read from this and say, well, that time appears to be about 4.2468 seconds. Well, then I zoomed in, and it turns out I can see here that that crossing time is about 4.7784 seconds. And I could have zoomed in more to get more precise, but that's actually how you solve these things. My last slide. From that graphical analysis, I find that it's 4.7783 seconds to complete the 1,000 feet run, and it reaches a maximum speed of basically 106 meters per second. Now, we started with real life numbers that in real life it takes 3.7 seconds to complete the race, and it reaches a maximum speed of around 148 meters per second. So was my model accurate to reality? No. So what would I do then to improve the model? Because we're out of time, I won't go through the process of trying to think how we would modify the model. But we did see the math of how we work through these things, which was an important part. The evaluating the model is also important, but not as. Did you have a question, Ryan, before we leave? No. Okay. So